Okay, welcome everybody. A lot of things to cover tonight, and I'm going to just to help relax you a little bit. I will send you the slideshow to your school Gmail account that you all have. Okay. When we're finished tonight, I will also send you the recording of this session, and I may have even posted it already in my Canvas class. But we're going to go through and review last two chapters, chapter 14 and 15. And before I talk about all this, maybe while you're kind of copying down, can you listen and copy things sort of at the same time? I'm going to review the end of the quarter, how it's all going to unfold here. Last week of the quarter is this week, okay, for everybody on across the college. Next week is finals week. On Monday night of next week, I will, what is it, 11, 12, 13, the 14th of June, I will still have Zoom and I will go over, like I've done the other two exams, I will go over the whole exam next Monday night. Okay. And then you can take your exam on Wednesday. I think that's about when I'm going to try to have you take the exam by is by the end of the day on Wednesday, like by midnight or something. Um, However, I suppose if you felt like you're ready, you could take it sooner than that. But so last week of the quarter, next week is finals. I'm going to review for the final the last exam next Monday night in Zoom. Okay. All right. You guys remember counting like this? So arithmetic sequences. Okay. The first concept we're going to talk about right now is what is, well, first of all, a sequence. What is a sequence? Okay. This idea of a sequence, okay, is the idea of a group of numbers. Whoops, hang on a second, guys. I'm gonna have to reduce myself. Wow. Sorry. Yeah, letting people in the class, which is very kind of me. Um, I'm not sure how I can bring myself back. There I am. Da, da, da. That's not it. Okay. So a sequence of numbers is a group of numbers in a row. So if I had, for instance, the sequence of 1, 3, 5, 7, okay? 1, 2, 3, we're adding 2 each time. We've got a sequence of numbers. So it's a group of numbers in a row. And so what they call in this chapter 14, an arithmetic sequence. Go ahead and turn your microphone off if it's on. Anybody, just go ahead and make sure your mic is muted. So an arithmetic sequence is where we're adding the same number each time. Okay. In my first example, 2, 4, 6, 8, you can see that we're adding 2 every time. We're just adding 2, and they're all exactly 2 apart. Okay. So they call that an arithmetic sequence because they're all in order, 2, 4, 6, 8. All right. Just so you know, you could be dealing with negative numbers, but adding 3 each time. If I have negative 8 plus 3, right, that gives me negative 5 plus 3 gives me negative 2 plus 3 gives me a positive 1 plus 3 is 4, etc. Okay. So that is an arithmetic sequence, is where we're adding the same thing each time. That's an arithmetic sequence. It's a term. You'll have it in your homework. They'll probably have some homework questions for this chapter where they'll give you a group of numbers and they'll ask you, is this an arithmetic sequence or is it a geometric? Right now, we're focusing on this slide just on arithmetic sequences for this slide, okay? So that's what an arithmetic sequence is. It's a group of numbers, that's a sequence, that are adding the same thing each time. All right. Now, as opposed to that, oh, I'm sorry. So what I want you to do, I'm going to give you a hint on your notes, how to make them kind of clearer, is to have in your notes the name of the concept, which is this right here, an arithmetic sequence, okay? And have the definition, which I'm going to move this out of the way some, okay? So we're adding the next number, it's the same, adding the same number, okay, to the previous one. That's the key concept right here. In fact, if this is all you copy down is the arithmetic sequence is adding the same number to the previous one, that's what you need. That is the concept. And then I gave you 3 examples, all of which are showing a sequence, a line of numbers, sequence, in sequence, all of which change by 2 or 3, or in this case, -2. I'm adding negative numbers to this, by the way, but it's the same. All right, now, so in your notes, have the concept. Think of these three things: concept, example, formula. Okay, those are kind of the three things you want to have bunched together in your notes together. The concept, the term, arithmetic sequence, an example, at least one example. You don't have to have all of mine. And then the formula that goes with it. And remember, I warned you about 2 or 3 weeks ago that, hey, we're in the last 2 chapters, we're going to get into some formulas, okay? So here's what I want you to copy down next. I want you to copy down the formula. This is the formula for an arithmetic sequence, okay? It's a formula that I use in investing, in banking, and research and all kinds of things. They have a formula. So this will go all next to arithmetic sequences. That formula is n, that's supposed to be an n there, okay, and we'll get into what that means here, equals the starting value, okay, in the sequence, the starting, so write this down right here, starting value, this is our formula, plus, and then in parentheses, boy, these, I really had some trouble writing here, plus n minus 1, just copy it down, don't worry about what it means, times the added number, N-U-M-B-E-R, the added number. So you got this starting value plus, in parentheses, n minus 1 times the starting value, the added number, okay? So hang on a second. I'm going to try to let somebody in. Come on. You can work, can't you? Sorry, it's not working very well. Give me a second. What did I just do here? Oh boy. All right, I might have lost somebody. Okay. So you got the formula. Hopefully you got that copy down here. So let me just show you in the sequence. Well, first of all, okay, you got the formula copy down right here. Okay, let's pause for a moment. I know you're really anxious to copy everything down, but we need to talk about what n means, the term n, okay? All right, so you need to be able to clear this. I would copy this down right here, this little thing I've got here. I've got a sequence of numbers, 2, 4, 6, 8, 10. Okay, they're all, this is an arithmetic sequence. They're all in order, adding 2 each time, okay? Now, if they asked you, you know, which is the first term in this, what is the n, the first term, they use the letter n to stand for it, okay? What's the first term? You'll notice I put numbers above them, okay? 1, 2, 3, 4. The first term is 2 in this sequence of numbers. What's the third term? It's 6. What's the fifth term? It's 10, okay? So in order, that is how they name the terms, first all the way through however many terms there are. So look down here as another example. If I had the x value, which by the way on a chart, that would be all my x values here, okay? These are all my x's, okay? Okay, and then my y values go here, typically on a chart. You know, our first term here would be if I had a list of numbers, okay, a sequence of numbers, the first number, that's my first term. The second term is my second number. So really on this chart here, it'd be this, and I should choose a different color so it actually shows up. Don't you think? My second term would be this one on a chart, okay? This is my first term, okay? All the way down through however many terms there are, okay? So what we need to know is that this, when they talk about a term, like find the 11th term in the sequence, okay? They're saying numbering from 1 all the way through however many terms there are, find the 11th one in the sequence. Is that kind of making sense? So the first term is this one, the second term, 4 is the second one. Likewise, this chart here is showing the term, first, second, through all the way through the 6th. All right, now, Let's go back to our formula, see if we can make a little bit more sense of it now that we know what n means. Yeah, it's whatever term we're looking for, okay? So our formula was n, whatever n we're trying to solve for equals the starting value plus the term we're trying to find minus 1, and then times the added number. Okay, so let's say in our sequence here, I'm going to choose green, just go to a different color here. Let's say that they gave you, the first, I don't know, a couple of terms, but they ask you for the fourth term here. They wanted you to find out what the fourth term is, but all of these boxes down here, 8, 10, 12, 14, etc., were all blank. We didn't know what they were, okay? So hypothetically, if they ask you if you had this sequence and it's an arithmetic sequence, 2, 4, 6, 8, adding 2 each time. If they ask you, use the formula to find out what the fourth term would be. All right, here's where we go to our formula. This fourth term is that we're trying to solve. We're trying to find out what is the fourth term, okay? So I'm gonna put a fourth here and a question mark, okay? What is the fourth term? It equals the starting value. What is our starting value? There's my first term. That's my starting value, okay? I'm gonna draw an arrow. Sorry about all these arrows. They're now gonna be going all over the place here. There's my starting value plus or minus. Now I say that because you might add a -2 each time. So in a sense, you're subtracting 2 each time, okay? So if we're adding, if you see that plus sign right there, you're probably looking at an arithmetic sequence in chapter 14, okay? All right, back to UR. Starting value plus, and then it says n minus 1. You see this part of the formula here? What is n? What is our n? We're trying to find the fourth term. That's the n, okay? So this would have been really helpful to have this kind of visual in the textbook that I had to read through 8 times to try to understand what they were trying to say in their own language. But so yeah, the term we're trying to find, minus 1 times the added number. Okay, well, so I got 4 minus 1 here. This is the 4. This is where n minus 1 becomes 4 minus 1 times, what's the added number each time? We're looking at the sequence, 2, 4, 6, it's 2, okay? So now let's simplify our formula. So I've got the starting value of 2 plus 4 minus 1 is 3 times 2 is 3 times 2 is 6, right? So this is 6. If I just do this, it becomes 6. Okay. So I've got 2 plus 6 is 8. Bingo. So our fourth term in the sequence, if they wanted us to solve for the fourth term, would be, if I used this formula, would give us to 8. And sure enough, looking at the sequence, oh yeah, it was 8. Now, somebody's going, well, teacher, why don't you just count them up in your head and figure it out that way? Here's why. In the investing world, banking and investors, and in a number of other kinds of mathematics and real life applications, they might invest, a group of people might invest a bunch of money into, like, say, an apartment complex. And they want to know in how many years they're going to actually start turning a profit, which means making money instead of having to pay out money. They start using formulas kind of similar to this, and they can predict in the future when they'll start making money instead of just breaking even or being in the hole, okay? So these formulas actually become very practical and powerful in the real world because if they ask you in this sequence, find the 200th term, you'd go, what, 200th term? I got to count all the way up by 2s all the way up to 200, the 200th term, and figure out what that is, right? But if they asked me for the 200th term in this arithmetic sequence, I could go n, that's 200, okay, equals the starting value plus 200 minus 1, right? The 200th terms, that's the n here, that's the n, this is the n, okay, times 2. And I could figure it out in less than 10 seconds. You see the value of these formulas? Okay. So what you got down in your notes is arithmetic sequence, adding the same number each time. And you have that there's a formula for it, okay? And you have an example of them, like this is an example right here. You have those 3 things together, bunched together in your notes. Let's move on. And this is another example. Okay, so I don't think you need to copy this, but just listen to it and see it. See it. So I've got an example. I've got a sequence of 7, 10, 13, 16, and 19. All right, 7 plus 3 is 10. What's 10 plus 3 is 13? I'm thinking, oh, this sounds like I'm adding 3 each time. Okay, so I'm going to write over here in green plus 3 here. Okay, I'm adding 3 each time in the sequence. But let's say I knew a couple of them and they ask you for the 5th term, okay? Tell me what the 5th term is, okay? Now, and like I said, it could have been the 15th, right? So I'm gonna plug it in my formula, which is n, in this case, I put a 5 here, okay? The 5th term equals my starting value, this is my starting value, okay? Plus, when I see that plus sign right there, I know I'm dealing with either what they call a arithmetic sequence or a linear one, which we'll get into in the next chapter in a moment. But we're dealing with plus or minus, so it's arithmetic. And then n, what term am I looking for? I'm looking for the 5th term, okay? So it's n 5 minus 1 times, what is my common adder each time? I'm adding 3 each time. So 5 minus 1 is 4, times 3 is 15, no, right? 4 times 3 is 12, okay? So 7 plus 12 is 19, okay? And so that is another example of just walking it through the formula of an arithmetic where we're adding the same thing each time. We're adding or subtracting the same thing each time. There might be a key concept you might put in your notes, is that it's this adding or subtracting the same thing each time, okay? That means it's arithmetic sequence. Okay, now in your notes, I want to really delineate, this is a new concept, okay? So maybe separate it a little space on your notes or something, and we're gonna put the 3 magic things together again in a geometric sequence, okay? A new kind of sequence, okay? All right. And you find that next term is found by multiplying the previous number by that term, okay? Those are the key words in the definition of a geometric sequence. Now I'm gonna slow down a bit, give you a chance to write it in your notes, maybe highlight geometric or underline it a couple times. As I mentioned before, I always try to train students for college and in college that when you're taking notes, always have like 3 colors of pen. And maybe one of them is a highlighter to highlight the key ideas. When I used to listen to so much of my degrees that I have, listening to professors in college was listening and taking notes and then taking midterms and final exams based upon how well I took notes and studied them. A lot of it was that in college. And so I got used to really good at a couple of colors of pen. And as the teacher was teaching key concepts, I might do in red. Okay. So every time I saw something in red on the page, I knew that's a key new concept. And I might highlight it in yellow also. And then just the details underneath it might be just blue. And then if there's something else special related to it, I might have those in a different color. So they all stood out because research shows we remember colored things better. Okay. Colored notes that are coordinated visually. So in addition to that, when the professor, who often happens, you ever have a teacher that they'll give a bunch of information or some information, and then they'll stop and tell a story. Okay. Here's what I was doing. I was listening with one ear to the story, but with not my other ear, but with my hand and pen, I was kind of quickly going back through what I just did and highlighting, make sure, to make sure it looked neat with my different colors. Okay. So it stood out. And then at the very end of the lecture, all the other students would jump up and start moving to the next class. I was often the last one to leave the class because I was like going through, highlight, make sure that visually with my colors and darkening things, I made it really clear what I was doing in my notes, okay? And then when I walked out of this is kind of strange, but when I walked out of that class, I'd actually studied for the final exam or the midterm a little bit, just right there by doing that. And research shows if you do something right after you learn something new, to review it, it helps you remember it better rather than waiting a day or a week, okay? And then when I went to study for the exams, I was so much more, everything was highlighted and visual, and it was easy for me to focus on what I needed to. So anyway, that's my little side note. So here we go, back into this. Here's the sequence. Okay, a geometric sequence is The next term is defined by multiplying. So in your notes, you see how I'm drawing a box around the word multiplying? Of course, that's times, okay? That's the key difference. That's when we know when I'm multiplying something by something, I'm dealing with, in chapter 14 here, I'm dealing with geometric sequences, which, by the way, grow way faster. When you multiply, things grow way faster. Like little rabbits multiplying, okay? You can get a lot real fast. All right, so geometric means the next term is found by multiplying. So you got in your notes that, oh, there's the key idea, it's multiplying. All right, here are some examples. So please have maybe at least one example. Example one is you've got you got these terms right here, okay? These terms, okay? 3, 9, 27, 71. 3 times 3 is 9. 9 times 3 is 27. 77 times 3 gives me, 71. So these are all in a sequence where the multiplier is tres. 3 is the multiplier, okay? And so because I'm multiplying the previous term, 3 by 3 gives me 9. Multiply this previous term by 3 to get the next one. They're calling this a geometric sequence, okay? A second example, and by the way, 3 is my first term, okay? My N1 in a sense. 9 is my second term. 27 is my third term, etc. Okay, term 1, 2, 3, 4. Here's another example. The sequence is right here. Okay, 2, 4, 8, 16. 2. How did 2 become 4? I multiplied by 2. How did 4 become 8? I multiplied by 2. I'm multiplying. My multiplier is 2 each time. Those are two examples now. So you got the definition. You've got the example of a geometric sequence. Guess what's coming next? Okay, if you're really paying attention, the formula. Here comes the formula. Okay, so in my notes, I want this together with what I've just been talking about. So I've got the nth term, okay, whether it's the 15th or the 50th or whatever term I'm trying to solve here, equals, okay, in a geometric sequence, the starting value, okay, this is the word value here. Sorry if it looks kind of crazy. Okay, the starting, oh, that's the same as it was in a arithmetic sequence, times. So what I'm going to do is take my red pen here and model like I used to do in my notes here, times here. I would have highlighted this and drawn red around it. When I see times in a geometric formula, I know this is a in a sequence. When I'm timesing something each time, I know that I am working on geometric, okay? Now, what am I timesing? The multiplier. And what did we say was the multiplier? It was like that 3 times 3 is 9. 9 times 3 is 27. So 3 is the multiplier, okay? That's what they mean by the multiplier. It's the number you're multiplying each time by the previous term. To the, okay, this is where it gets a little bit algebraic, I guess, to the n, so whatever term I'm trying to find, minus 1. So this is an exponent, okay? So I'm going to write this down here. You might want to put this is an exponent here, okay? I'm just reminding myself visually that this is an exponent here, like 4 squared. That's an exponent, okay? That's an exponent. This is an exponent, okay? All right. So let's kind of go through here and let's look at our sequence here. I've got an example of 2 times 2 is 4, 4 times 2 is 8, 8 times 2. So the multiplier, okay, is 2, obviously. Equals 2 every time. That's my magic multiplier, okay? So let's say that they ask you, well, using the formula for the geometric sequence, find the third term. So I'm going to do the exact thing I just got through doing on the previous thing. I'm going to plug it into my new formula, n, okay, in this case, n number 3 here. I'm looking for the third term, so I put a 3 down here. They don't usually do that, but I'm just visually to kind of make it clear. My third term here, I'm going to just draw an arrow here. Uno, dos, tres. See how this is term 1, this is term 2, this is term 3. You guys getting this by now? When they ask for n, they're asking which term it is. So times my starting value, okay, my starting value here, okay, is 2. There's my starting value. Notice that it's right by parentheses here. It's right next to it. That means times. Okay, we've talked about this. So times, and then it says the multiplier. Well, here's my multiplier. Okay, got all these arrows going all over the place here. There's my multiplier to the, like squared or cubed, right? To the, what does it say? It says n minus 1. What's n? Tres. So 3 minus 1. Okay, that's writing it all out. Now let's think this thing through. We've got the third term in the sequence would be the starting value times, that means geometric, the multiplier to the exponent of the term, the n minus 1. Okay, the n is which term we're trying to find. In this case, third term here, okay? All right, so do the math up here first. 3 minus 1 is 2, right? So this becomes 2 squared. 2 squared is 4. So I got 2 times 4 is 8. Okay? That is plugging the whole thing into the geometric sequence formula. Some of you are thinking right now, hey, teacher, you're giving me 2 whole formulas. How am I going to remember all this on the test and my homework? You're going to remember it all because you're going to have the examples in front of you, you're going to have the definition in front of you, and you're going to have the formulas in front of you. You don't have to memorize them, okay? You will have them with you both on your homework, and you will have them with you in the on the exams or the exam, okay? Here's another example. You don't have to copy it down because it's the same thing, but please listen through it. Sequence, I got a sequence in number 5, 15, 45, 135. 5 times what got me 15? 3, okay. Then 3 times 15 is 40. Oh, it looks like I've got a geometric sequence going on here where I'm multiplying the previous term by 3 each time. Okay. If they ask you to find, in this case, I circled 4, so the 4th term, okay? If they ask you to find the 4th term, and again, like I said, this could have been the 14th, right? They could have asked you, and they will in your homework, find the 12th term. I do my starting value, n equals, this is a 4th term. I'll put this over here. Well, this 4th term here, okay, is equals my starting value, that's my starting value, times, you'll notice it's right next to it in parentheses, which again means times, my multiplier, which is my 3 here, okay, to the n, the term I'm trying to find, minus 1. I'm trying to find the 4th term. So that means 5 times 3 to the 4 minus 1 is 3. That n is the 4th term, okay? So that is, I'll draw an arrow here if that helps you visually to connect the dots here. It's my 4th term. All right, so 4 minus 1, so 4 minus 1 is 3. So 3 to the 3rd is 3 times 3 is 9 times 3 is 27. Okay, this equals 27. That's 3 cubed, if you want to say it that way. 5 times 27 is 135, right? Looks about right, okay? So that's an example of geometric sequence. Okay, so we've talked about arithmetic sequence, adding the same or subtracting the same number each time to the previous term. We got the formula, the definition, and an example. We've got a geometric sequence. We're multiplying. That key thing we said right here was that we were multiplying right here. We're multiplying. When we're multiplying, it's geometric. All right. Now, I'm going to jump to kind of a new concept before we jump into chapter 15, okay? 2 different kinds of reasoning, and you'll have like one question like on this, on your exam 3, okay? And I think the best way to try to understand it is just to maybe try to draw this picture over here to the right on your notes. So I'll give you like a whole minute here to just minute or two to copy it down. Okay, 2 different kinds of reasoning. All right. What is the difference between inductive? Inductive. I'm looking at the word itself. Okay. And then you got deductive. Okay. All right. So we'll start with inductive. Okay. In inductive, it says it starts from the specific facts and then it moves to a general principle. Okay. General principle. So like in science, if you went to out in the woods in Snohomish and you found a pond that had all kinds of frogs that had 3 legs instead of 4, and fish that had like weird things going on, and you start looking at all these things going on in the pond and they're abnormal, okay, all these little specifics about that pond, you might start moving to some general hypothesis or about what's going on with this pond. And probably the first one comes to mind is there must be some kind of pollution or weird chemicals that are getting into this pond, right? These aren't from an alien spaceship, 3-legged frogs, but maybe there's pollution that's really causing problems. So the general principle is there must be, or hypothesis must be, that there is pollution, but all the specific details, 3-legged frogs, fish missing a gill, other plant life and other kinds of things all messed up, not normal, okay? So those would be the specific details. So when you move, okay, so inductive starts from the specific facts, okay? So these specific details, the frogs, the fish, the other wildlife, the vegetation, all these things all messed up. Then you move to a general principle that, oh, there must be pollution here, okay? A general principle. That's inductive reasoning. We're inducing from the details, we're inducing a hypothesis, a general principle, okay? So you're starting from the specifics, moving up to the general, okay? So that's why there's this arrow here. You'll notice this big arrow here. Starting. So when you move from the little details, think of the little details on the ground here, okay? Okay, little details on the ground, okay? Okay, and that word might help you to remember here. This word ground here, okay? Think of them on the ground here, all these little details, okay? Specific instances, okay? And when you move up from that into a theory or a principle, moving up to a theory, okay, or a principle, that's inductive reasoning, okay? Conversely, deductive reasoning starts from the general idea, starts up above, okay, the general principle, and you move down to the specific, okay? Now, teacher, what would that look like then in real life? Let me go back to my warped 3-legged frog pond. And let's say that you noticed, like has happened on Lake Washington between Bellevue and Mercer Island in Seattle, especially used to happen back in the 50s and 60s a lot. Some sewage pipe would get loose and it would release a whole bunch of sewage into the lake, and sometimes chemicals, and it started affecting the fish and then other wildlife, and weird things might happen to them. If you, big picture, you realize, hey, a bunch of chemicals have been released into Lake Washington, you might then go from the general, okay, here's the big thing, there's a bunch of pollution there now, to what all the specific consequences going to be. Salmon that's polluted and is not the right color, and various other kinds of things that might be happening in the lake that are abnormal. All the specific details on the ground might be affected. Okay, so I think that's about as good as I can do to try to explain the difference between the two kinds of logic. We're not going to spend a lot of time on that. There's like just one question on it, okay? But moving on. All right. All right, so this slide, you want to take a moment or two and just take your time, see how things in color. Go ahead and copy it down. All right, so this is just kind of a review slide in a sense, okay? And the review idea, which we're going to get on in the next, you have independent variables, okay? And those are usually the variables that are on this line here. They're on the X line, and we'll see that in a moment. And then the dependent, they're dependent, like how many hours of work, hour 1, 2, 3, 4, 5, determines how much pay you get over here. So pay is my dependent, dependent, okay? All right, so that's the difference between the variables, okay? And this is my independent variables. Independent because it's not dependent on anything. We're just doing it to affect how much pay you get, okay? So the X and the Y, okay? And so that's the two values. You got the two lines here, the X axis and the Y axis, okay? Sometimes now they're going to start calling them, however, this word right here, you probably do want to write down here, okay? They'll call this output This is the output here. Whatever happens, how much pay you get is an output of how many hours of work you put in. Okay. Or if this was hours of sunlight on plants, and you notice the more sunlight the plants got, so hours of sunlight a day is the independent variable. What is it affecting? It affects how much growth that the plants might get. Okay. How many hours you studied will affect your grades. That's dependent upon it. So the output they're going to now start calling in chapter 15 in your homework, and in the text, they call that a function of, or a result of, the x. So this word function means the same thing as result. Okay. Your pay is a function of your hours worked. Your grade, the dependent variable, the output, the grade that you get in a class is a function. It's a direct result of how many hours you study. Okay. The growth in the plant is a function of number of hours of sunlight per day. Okay. So it's a function of the x in a sense. It's a result of the x. So for instance, 2 hours of study has a direct function. It affects a certain amount of results in grades. Okay. This slide, the two key concepts is, I want you, just like we were doing before. Remember when we had three things? We had the term, an example, and the formula. Okay, I want you to think like that in your notes. Linear growth, this is the term. Okay, and here's the example. Okay, so I'm going to give you a few moments to copy down this slide if you don't mind. Let's talk about what this means. So our concept is linear growth, and our example is it's growth. So it's growth in a line, in a sense. That's the definition, in a line. Okay. By the way, look at the term itself, linear. Look what it has right in the word itself. It's got the word line. Okay. So that's visually a way to try to remember it. Linear means line. It's growth that's in a straight line here. So you'll notice if you see a chart like this here, and it's got growth, it's showing growth, and it's all in a straight line, that's linear. By the way, arithmetic growth, 2, 4, 6, 8, 10, 12, would be linear growth. Okay. Now, and then by the way, in case you you run into this in homework, any questions, linear decay would be, it's in a line. Okay. It's linear, so it's in a line here. Okay. This word line here with this word here. Okay. If it's getting less, it's declining, like you're losing money every year, or the amount of, for instance, right now in our country, the amount of COVID cases is on a linear decay. It's going down. I think, like, I forget what it was, every week now, 500 fewer people than before were getting COVID. Every week, in several weeks in a row now, 500 people less are getting COVID. So it's, in a sense, it's decaying. The number is going down. Okay. All right, here's our formula. Okay. So we've got a formula, and now they're going to start calling that the function. So I wanted to put the idea that this word, if they ask you if they're talking about the linear function or the exponential function, that means kind of what in my mind, it's just the formula. Okay. That's what that term is it's the formula here. Same thing. Okay. Now, do you remember I said earlier, I talked about the function here. Look over here on the far left here. We've got the function, this y value here. This is the y value, okay, the y-axis. It is a function of a result. Remember, it's a result of how much input goes into something, the amount of input that we're putting into something, which is the x. Okay, so y is a function of x. Okay, so if they wanted to know in linear growth, okay, 7 years out, for instance, in linear growth, what would the y be? Or 14 years out, or 40 years out, what would be the function result be of doing something, okay? That y, that result, that function over here would be here's my magic formula. Notice all of them start with this term right here, starting value, okay? So if this was 2, 4, this is years, 6, 8, 10, etc. Okay. Then it would be my starting value would be 2. Okay. Okay. Plus, okay, plus is linear. Plus or minus is like linear. It's the same thing kind of as arithmetic growth. Okay. The rate of change, which would be in this case 2, right? Times the independent variable. Okay, the rate of change is 2, 4, 6, 8. It's going up 2 times each time. Times what's the independent variable? That's the x. Okay, so in parentheses down here in my notes, I'm going to add the word the x. Okay, the x value. So that's this number along here. Pick the 1, 2, 3, 4, 5, 6, 7th term. Okay, if this is the 7th term here, then that would be the x, 7. This would be a 7 over here, okay, for linear growth. All right, that's the formula for finding linear growth is starting value plus the rate of change each time times whatever number variable it is here on this x-axis, okay? Let's take a look at an example. So remember I told you in your notes, concept, example, formula, okay? So let me give you a moment or two to copy this down and then we will try to explain it to you. All right, so the first thing I want to do is remind you of a couple things. The x, see how you'll start seeing this in algebra, okay? The x is, just as a reminder visually on our chart, it's this line here, it's this axis here, okay? So again, time in years studying or hours studying or years working for a company, so you get raises like Boeing, where on the 5th year you get a big raise in a lot of positions. The x value and the y value, okay? All right, and so the y, so let me show you what this actually is talking about, okay? So at 0, let's say we started at minus 18 here. In a sense, this would be like 0 here, guys. Here's 0. This is minus 18 right here, okay? I'll put a little circle right there, a little dot here, okay? At 1 month or 1 year or whatever, 1 quarter, okay, it's minus 12. So I'm going to write this on this little chart here, minus 12 here, okay? After the second year or the second quarter or the second hour of studying, okay, it's minus 6. After the third, whoa, we got 0. And then after the fourth, it's 6. So you'll notice, in this case, what am I doing each time? It starts at 18. It gets, this is actually getting bigger each time. You know that negative 18 is a lot less than 6, right? I'm adding I'm adding 6 each time. 18 plus 6 gives me negative 12. Negative 18 plus 6 is negative 12. Negative 12 plus 6 gives me negative 6. Negative 6 plus 6, I'm sorry, plus 6 is 0. 0 plus 6 is 6. So we're adding, my rate of change is 6 every time, okay? All right, so if I wanted to find, let's say this is linear growth, because this is what this is, okay? We're talking about an example of linear growth here, okay? And a line here, okay? I'm gonna just add the word linear, okay? All right, so to find the growth at, say, whatever point it is, you know, the y, to find the y value up here, whatever this y value is, okay, amount of pay or grades or how much growth the plant got, we would plug it into our formula. Y would equal our starting value, which in this case, the first value we have is negative 18, okay, plus, that means it's linear growth, the rate of change, which is 6 each time, okay? 6, I'll write this here. Every time it changes 6. Times, that's the times, And then this x is the independent variable, whichever number we're trying to solve here, okay? The independent variable. So that is our formula for linear growth. Just reminding yourself in my notes here, it's the same thing you already wrote down. Function, now they're calling it a function, because really y is a function of x, or in parentheses, I'll just put down, I see it as the formula. It's the magic formula for finding this out, okay? All right, let's jump to the next big concept, okay? Which, no, actually I have another example. And I have a little note here reminding you that if you're adding or subtracting, it's linear, okay? So, so let's say that the X stands for months, okay? And Y stands for the amount of money that you have left to pay on a loan, okay? You don't have to copy this because you've got an example. If you want to, you can. But at month 0, when you first start off, it's an $800 loan, okay? You borrowed $800, okay? But you're paying, let's look at it, 50 to 750, that's 50, that's a change of 50, minus 50 is 700, minus 50 is 7. I'm subtracting minus 50 each time. This is my rate of growth or rate of change is minus 50, okay? So the left to pay, that's how much I still have to pay, is my Y. So if it was on a chart, it would be like this. Well, I'll just do a couple of months. 1, 2, 3, 4 months of pain. I'll say paying back a loan, okay? Just to be a loan of money, okay? So this is 1 month, this is after 2 months, 3 months, 4 months. When we started off at 0 here, at this 0 here, we owed $800, okay, at 0. That's what, putting it on the chart here. And this is my Y value, okay? This is my Y value. So if we wanted to find out how much I would owe after 7 months, say for instance, okay, I could find my Y, 7 months, okay, Y equals starting value of $800. There's my start value. Minus, because remember I said the rate of change is either plus or minus the same number every time. Minus 50 times in this case, let's say I asked for the third month, okay? So this is be the third month. And we want to know how much would I still owe after the third month? Then that would be my independent variable, okay? So I apologize that it seems like a lot of formulas here, but it's like there's 2 in each chapter. But it's really building towards this idea of finding the Y, solving for the Y here. Because what they might give you is, they might give you the first 3 terms, but then they might have blank spaces all the way down to 10. And they might ask you, find after 8 months, how much you would owe, okay? You could plug it into this formula for linear growth. Okay, this one we need to pause. This is kind of our last concept, I think, here for the night. Okay, folks, I hope I've given you enough time. So here's our concept. Exponential growth is where increase or decrease, so sometimes it can be decay, by a constant multiplier. In your notes, do what I'm doing right here, okay? Highlight this, multiplier. So adding or subtract, equals linear. We just got through talking about that, okay? Multiplying equals EXPON, okay? Exponential, okay? Exponential, okay? Growth. So by a multiplier, as the inputs increase by 1, okay? So On the left, you see a chart there that says it's got here. My hand just kind of cranked up. You see how this it goes like this? You'll notice it's not in a line anymore. That's a classic example of exponential growth. Okay, and this is how people who get wealthy, they start off, they invest a lot of time and energy and money and sweat and blood and stress in something. And at first they're making no money, sometimes for a couple of years, and they're losing money. But they're taking the risk that the whole thing could fall apart. You know, they say like 90%, I forget what it is, of small businesses that start, they fail. Like the great majority of small businesses fail. So there's a lot of people out there that tried something, they invested their heart and soul in it. They might have put a second mortgage on their house, sold their car, all this stuff, tried it for a few years, and then it collapsed and they lost everything. They risked everything. But in exponential growth, it's where they are taking the risk because they know it, if it starts going at a certain point with exponential growth, if I'm timesing, 20% each year, I'm gaining 20% each year. I'm times 0.20, which would actually be technically 1.20. That'd be 120%. Growth each year. At some point, those numbers start getting big enough that the growth starts going up like this, and we start really growing. Okay. So it's a big risk, a lot of sweat and tears, and most people are not willing to fail and try like this to invest in things. They just aren't, because it's too risky. They like something more safe. Okay. Um, Likewise, exponential decay would visually look like, this is an example of what it would look like, is kind of this arc here until it's just really falling off. Okay. And notice they start at first like there's no change hardly at all, and then it just gradually starts, and then it starts accelerating. Okay. All right. There's the function. Okay. The formula. Okay. For exponential growth is the y. Okay. This again, this y value here, really trying to hammer this into you guys' head. X and y. What are we talking about? This result. Okay. How much money I still owe, or how much money I'll be making, or whatever it happens to be. This y value equals, whichever one we're trying to figure out, the starting value times, you see how I said that it's by a multiplier? There it is right there, the times, the multiplier. That's the difference between linear, which is adding and or subtracting, and exponential, which is multiplying. Times the multiplier, we figure out what the multiplier is. If I multiply 3 each time times the previous number, 3 is the multiplier. To the, okay, you see how we have an exponent here? The independent variable. Okay, hopefully you have this copy. You know, what is the independent variable here? That's this number over here. It's the x value. Okay, the x, whether it's 6, 5, 4, 3, 2, whatever it is. Okay, that's the independent variable. So the formula you'll have in your notes for homework and for your exam for exponential function is y equals the starting value times, it must be exponential, the multiplier to the whatever the exponent is, whatever the x value is. Okay. Let's look at an example or two here. Okay, let's kind of see an example. Whoops, went too fast, too far here. Here's an example. Okay, so we're talking about, let's say we're talking about unfortunately, to have to bring this up, some kind of an outbreak of a flu virus or something. Okay. And so my x values, this is my, here, let me choose a color that hopefully will show up. This is my x value. Okay, on a line. This is my x. Okay. Okay, this line of things here. Okay. Day 0, okay, you haven't started counting yet, but you notice you had the number of people infected that day, okay, just on the first day we happen to look, okay. After we start counting from day 0, okay, the first day we notice, 1 day later, we notice we have 200 people infected. This sounds like an outbreak, okay. The second day, after 2 days, we have 400 people infected. All the way down, you see it's doubling each time. So what is our multiplier? Our multiplier is 2, okay? Each previous number is multiplied by 2 to get to the next term, okay, the next value. So if they will ask you, hey, we're noticing that we're having exponential growth here, where we're multiplying by the same number each time. How many people are going to be infected after 14 days, right? After day 14, 2 weeks, okay? That'd be my y. We're trying to find out how many people, okay, would be infected, equals my starting value, which is 0. We started with, this is my start value. Okay, if I wrote this on here, okay, times, times means multiply, means exponential. My multiplier, which is 2 here, this is my 2 here, to the exponent here. Okay, I'm going to go back one slide real quick on you guys here, to the independent variable, whatever the independent variable is, right? So let's say in this example, it was, they're asking you for how many, after 4 months, okay, how many people would be infected with this flu virus. So that's my exponent. That is my exponent because that's the formula. Starting value times the multiplier to the x, whatever the x is. This is my x. So I know that, what is all of this stuff here? I'm just giving examples of exponents here. That's what I was doing there. So on a calculator, I think I know what it is. Yeah, this is on a calculator to figure this out. What if they ask you for like 2 to the 4th? How would you do this on a calculator? You would, if it's 2 squared, okay, 2 squared, you would press 2, and then you have a key on your calculator. It looks just like this, and if I can find it here, looking at it. Yeah, here it is. I've got it on this calculator as well. Let's see if you can find that little x squared thing here, okay, on my calculator. Hopefully you can find it. You can hold this up right here. There it is. It's right next to the 7, just to the left of the 7, but probably to the right for you guys, okay? So that's when you're squaring something, okay, on your calculator. This will help you with your homework. So if you're squaring something, hit the number and then that key there, and it'll square it. So if it was 7 squared, you would hit 7 on your calculator, and then you'd hit that little key that looks like this x squared, okay? All right. Now, I'm just trying to, you also have a key, a down arrow, up arrow key. Yeah. And I'm forgetting what I did that for, but there's a way to like the 7th, if it was to the 7th, like 7 to the 7th power, okay? There's a way to punch that into your calculator. And I, for the moment, am kind of losing that from my calculator, what I did here, but where you can punch that key and then 7, and it'll do 7 to the 7th, okay? All right, and that'll make it a lot faster for you. So just know that you can do exponents on a calculator to speed this little process that I'm circling up, 4th or 7th or 20th, whatever it is, okay? All right, so that's an example of punching it through, putting it into the formula to find out how many people would be affected on the 4th month in exponential growth. Why is it exponential? Because it's multiplying each time by the same number, okay? We are done. I can't believe it. I hope you found this helpful, and it was a lot to cover in one night. So send me an email if you have a problem or a question.